Hello, everyone. Good morning. And welcome again to the JKMRC Friday Morning Seminar Series. On behalf of the University of Queensland and the Sustainable Minerals Institute, I'd like to acknowledge the traditional owners and custodians of the lands on which we meet today. We pay our respects to the ancestors and the descendants who continue cultural and spiritual connections with country, and we recognize the valuable contributions to Australian and global society. So for this seminar, it's my pleasure to welcome Professor Quentin Campbell. Quentin is a professor at Northwest University School of Chemical and Minerals Engineers in South Africa, has over 40 years of experience in academia and industry, and is a registered professional engineer with the Engineering Council of South Africa, and a NRF C1 rated researcher. He has published over 50 journal articles and 100 conference papers, and his research focused on mineral processing, particularly responsible coal processing. Recently, he was appointed as a part-time principal research fellow at the JKMRC. Today, he'll be presenting a seminar titled Magnetic Cyclones. So let's give a warm welcome to Quentin. Thanks, Quentin.
Thank you. Thank you, Daniel. Good morning, ladies and gentlemen, and those online as well. It's a surprising audience. There are a couple of faces here that I didn't expect to see that I'm very, very glad to see. Some of my collaborators on this project as well. Hearty welcome. The approach this morning is going to be that I'm going to be telling you not a lot of what we did, but also what we are going to do in the next year and a half, and the very reason why I am at the JK Center. Just so let's start off with the context. I've been involved with this work on magnetic cyclones for many years. I was approached in the 1990s by Jan Swoboda, then of De Beers, with two students, and he said, you know, I read about this magnetic cyclone for dense medium cyclone, and you know, we started from there. This developed through the help with the help of students up to a patented process. It was on ferrosilicon systems for diamond processing, and the technology actually went into the production stage. So they were running these cyclones at some of the De Beers operations for quite a few years. And then for some reason it died. And I'm not going to say why. I think it's operator resistance or something. I'm not sure. And also cost. In 2015, I was approached again by Multotec, South Africa, and they said they would like to test this on magnetite for coal systems. There were some papers around, and we read it, and we said, okay, Multotec, they're into cyclones, they manufacture cyclones. We said, let's try it. And I had a postgrad student, a master's student on there, and as far as students go, they never they never do what you say. So she came up with results, very good ones, but there are so many questions still remaining because instead of having 5 points on a graph, she had 2 points on a graph and things like that, the classic mistakes. But it was promising results in any case. And then we started talking about ACARP, and ACARP we applied with the help of Christian. We applied for the project and it was awarded. And the project kicked off 2 weeks ago, and that's what I'm doing here at the moment. We are going to pursue this, what we learned in the past. We're going to show that and distill that and refine that. So I'd like to acknowledge the collaborators here, and quite a few of them are in the room. You can read the persons there. A lot of this is in-kind contributions and financial contributions as well. Right, let's talk about the dense medium cyclone. Now, unfortunately, again, I see people here where I'm going to bore them with how a dense medium cyclone works. Hopefully, there are some people from other backgrounds who might not know all the buzzwords on a dense medium cyclone. Dutch state mines patented this in the 1940s for coal beneficiation, although it can be used for any dense separation or dense mineral separation based on density. So let's let me just see if I can, whoops, get the laser pointer going. There we are. Apologies for that. There we go. So it's a very simple piece of machine. It's really a cylindrical barrel plus a cone, no moving parts. And you feed the material under pressure from one side. Material is a mixture of the ore that I'm trying to separate as well as medium. And the medium I'll talk about later on. It's a suspension normally of a magnetic medium like magnetite or ferrosilicon. It goes into the cyclone and it starts spinning around. And because of centrifugal force, you've got settling as such through the medium, the dense medium, and the heavier minerals would then fly towards the outside, and the lighter minerals doesn't really stay on the inside, but as the cone tapers down, there's a bit of a crowding effect. So the lighter particles are being pushed up in through that inner core to the overflow. So essentially you end up with two products. You've got your more dense materials at the bottom, and the overflow through the spigot, you get your lighter material. Diamonds, it's nice. Diamonds are heavy. You want them in the bottom. For coal, the good coal is light compared to the other minerals, so you want your coal going to the top. So it's two different approaches there. It's different from gravity separation, because gravity separation is just something settling in water under the influence of gravity, where here you've got another force, a very powerful force, which is a centrifugal force. The medium is normally magnetite, ferrosilicon, suspensions. You want it magnetic because it's an expensive item, and the material has to be magnetic so that you can recover the medium after use back again into the system using magnetic separators. Must be stable, it must be inert, it must be relatively low cost as well. And the nice thing about that is because it's a suspension of fine solid magnetite in water, you can just control the density by dilution up to a point, of course, because there's another thing that comes in there, and that's stability. The more water you add, the lower density, you've got stability problems. In other words, your settling becomes an issue because it is still a suspension, and the material, the solids, magnetite, will settle from solution. And that's the problem with chasing low cut points. I'll come to that later on. You've got stability issues because of the medium. You can control the cut points up to a certain stage by various things. Important to note that the cut point, in other words, where I cut the minerals, what density, is higher than just the medium density. If I put medium density in there, 1.8 or something, my cut point will be higher than that because of the centrifugal acceleration. Some buzzwords. The dense medium performance is defined by the partition curve. A partition curve is really just a recovery curve to one of the streams. In this case, the red line shows how much, or what fraction of material is reporting to the underflow, the heavy in this case. For coal, you can actually turn it around, so the S will go the other way, because we are interested in the product on the light side, but it doesn't matter. The two are just mirror images of each other. So in an ideal case, the green line will show, if this was a perfect separator, what would happen? You would have nothing going to the one stream up to a certain point, that point being the cut point over there. And the mouse doesn't quite work on a carpet. And up to above the cut point, you will have 100% of the material going to the other stream. Of course, in real life, it doesn't work like that, and you end up with something like the red line. And the red line is the real case, and you can see that there's a lot of misplaced material. In other words, all the material in that area there, between the red and the yellow and the green lines, are all misplaced materials. In other words, they shouldn't be there, and that is the efficiency. So we've got various ways of defining the operation. The one is the cut point. That is the point at which 50% of the material, or material of that density, has got a 50-50 chance of going either up or down. The other one is the misplaced material. I've just shown you that, and that can be defined by the EP. EP is essentially the slope of that straight part there. EP runs between those 2 points there, and that gives an indication of the sharpness of separation. Of course, a small EP means the number means your line is more upright, sharper separation, and a low EP or high EP means a low sharpness of separation. So just a low number is good in this case. It's like a golf score. The medium and the density differential. Now, the medium particles themselves in the suspension, the ferromagnet, the ferrosilicon or the magnetite, are also subjected to the centrifugal force. So you will have a certain degree of settling or separation of those medium particles as well. And that means you've got a density variation over the area of the cyclone as well. As the medium particles fly towards the outside, you will have a concentration of densities on the outside as well. Now, this is either a good thing or not a good thing. A little bit of density differential is good. You don't want zero density differential, but you can also have a very high density differential, because you can imagine if the difference between the inside and outside of the cyclone is too large in terms of density, you will have a lot of middlings, particles that can't make up their mind, that's stuck in the inside. And that causes, all sorts of inefficiencies and go either up or down. Wear. That's what we found at the De Beers mines, is there was a lot of wear in the cyclone because these middlings are just sitting in the cyclone, eating up capacity and not going anywhere. So there's this density variation. Density differential formally is defined as the underflow RD, or the high relative density, minus the small relative density. And it is used as a proxy for sharpness of separation. Normal range, 0.2 to 0.5. If it goes higher than that, you've got a problem. If it goes lower than that, I believe you've got a problem, Tim. You've got to help me on the low, low density differentials. But that is the normal operating range, that density differentials. And as I said, the middlings are trapped in the zone there somewhere if this density differential becomes too large. Okay, now what do we do with a magnet? This comes out of the first papers. And what we do is we take a solenoid, magnetic solenoid, electromagnet, and we stick it around the cyclone in some position. And the position is very, very important, by the way. I've just drawn it in here around the barrel, but actually it works best if it's a little bit lower down. We'll come to that. And that imparts a magnetic force on the magnetic medium particles inside the cyclone. And that gives you one additional control. It does affect it. And if you can see it on that side, the resultant force changes. So if I change the current going through the electromagnet, hence I change the magnetic field inside, the medium particles will behave differently. And I'm hesitant to say better or worse, because again, that depends on what my setting is. So it gives us one more thing. And what was found is that way back in the 1960s, they used a magnetic cyclone with permanent magnets in Russia, where they recovered roasted magnetic iron ores this way. And they found that there was, something happened. I'm not sure everybody understood what happened, but something happened. In the 1980s, there was some sand magnetite mixtures that was used, that was separated using electromagnets for the first time. And these are all the leads up to the work that we did in De Beers. So Jan Swoboda contacted us and said, listen, I've read about these things. Can we try it? And we said, yes. So we put a solenoid electromagnet with a variable power supply around, first of all, 100 millimeter laboratory scale cyclone. I had a postgrad student there, and it was promising enough that we could patent this one in three countries. Then we erected or used a 100 millimeter stainless steel cyclone at the De Beers campus in Johannesburg. And I had another postgrad student who worked on that as well. It's very important at this stage to know that your material of construction of the cyclone must be non-magnetic, otherwise it's defeating the object. And that's why we're talking about perspex, we're talking about polyurethane, stainless steel, and you'll see in the new cyclone how we're going to manufacture that as well. So we can't go the normal mild steel, and that's where the cost comes in as well. And that's probably one of the issues that we have to look at, the advantages versus cost of manufacturing, because it's not a bulk manufactured item, not for the bigger cyclones in any case. Then this was implemented on the Koinas prospect plant. There was a bigger cyclone at 250 mil. It ran very well. Again, I had a postgrad student on that one, and it went to production stage, 510 cyclones, fairly big. And that was, we manufactured non-magnetic stainless steel cyclones with ceramic linings. Once again, non-magnetic is the magic word there. And this it ran actually very, very well. Similar cyclones were later used in the Botswana operations. And again, it ran. And then for some reason, it just stopped. And I said just now, tongue in cheek, it's operator acceptance. I think it was more cost of replacing these cyclones, because to have them made specially, I think that was one of the issues. All right. So the results were very, very interesting. We saw that the density differential could be directly influenced by the strength of the magnetic field, hence, the apps that we put through there. And we tried the cyclone in different, the solenoid in different positions around the cyclone to see whether towards the cone will it work or not. And all this work came out in a fairly nice report. In fact, quite interesting, we could actually achieve density inversion at a very high magnetic field strength inside the cyclone, where you would have in your overflow a higher density magnetite than at the bottom, or medium at the bottom. Obviously, you don't want that. So in general, the higher, up to a point, the higher the magnetic field strength, the lower the density differential, which is quite nice, because if you lower the density differential up to a point, you can potentially improve the efficiency. The EP could be improved as well up to a point, and that point where it goes back up again was actually, we suspect, the point where your density inversion started happening. So you could bring the EP down. Remember, EP, low number, high efficiency, or better. We found that the optimum solenoid position was around the upper cone, and that's not surprising. In other words, that's just below the barrel section, cylindrical section, where the cone starts, because that is more or less where the vortex finder, in other words, this pipe that grabs the overflow, is positioned inside the cyclone. And I would think that that is where most of your separation takes place. In other words, that's the hot spot where I can influence the separation. If you move the cyclone back up, the solenoid up, you are beyond the vortex finder and nothing will happen. And if you're too close to the cone at the bottom, it doesn't really happen either, because your separation has already happened in the cyclone. And the cone is really just a spigot, or the bottom part of the cone is just a spigot. So I think we found the sweet spot there of the position of the cyclone. We're not finished there yet, but I'll show you our design just now. And this was interesting. The cut point lowered significantly with increasing magnetic field strength. Now, in the diamond industry, that's bad news, because you can lose diamonds that way if your cut point is too low. But for coal, we didn't even think about coal in those days. For coal, it's actually a good news, because I'll come to the reason for that later on. So there is an effect of the cut point density. It's not clear, I must say, at this stage, and I'll come back to that. So also interesting, and this is just an aside, the effect of the magnetic field on the medium with and without the addition of ore was basically the same. So the same happened, the trends were the same. So whether you just run a cyclone on magnetite, or in this case ferrosilicon on the medium, or whether you add the gravel or the ore in there, the effects were the same. So the presence of any rocks in there didn't have an influence. It changed the numbers a little bit, but not the trends. There was a recent paper from China, magnetite systems in coal beneficiation, which is moving into the right direction now, where they use the 150 mil polyurethane cyclone in a closed circuit. But for some reason, it looks as if they positioned the solenoid in the middle of the barrel section. And very surprising results came out, which I'll show you now. They did a lot of work, and this is hard work. They used 3 coal fractions, and they did densimetric analysis on all those coal fractions separately. Now, I can tell you that to do a densimetric analysis on a -5 millimeter particle is just, it's murder. It's very, very difficult. So I admire the guys for the work that they've done. Medium SG they ran was about 1.3 to 1.4. analyzed all the products, and this is what they found. First of all, again, you can see the lines. The black line on the curve is no current, no magnetic field, and as you increase it, it moves towards the green line. In this case, in all cases, we found, or they found, an increase in the cut point, which is bad news now for coal. It's good news for diamonds. But what you could find, and you've got to really look at this because there are not a lot of points on these graphs, but the EP seemed to have improved up to a point in all cases. Now, that again is I'm glad to see Chris is here. That's the problem with these partition curves. If you're going to do tracer tests or density tests, you must have a lot of data points in that upright part of the graph. Otherwise, it's not going to show a lot. You want more points there. But in this case, it would have been difficult because you are limited by the density fractions that you can analyze for coal. And that accuracy of that line gives you the EP. So the EP numbers here, I would probably, it's interesting, but I would take that with a bit of a pinch of salt. Not saying it's wrong, saying that we should check that. So there was an increase in EP, especially on the coarser sizes. The fine sizes are, that's the graph on the right-hand side. That's a bit of a difficult one as well. But there was an improvement, but there was an increase in the density cut point, which is what we don't want. Okay, so my suspicion is that was the position of the solenoid. Okay, now the most recent work when we started getting back into the game was Multotec South Africa came up and they said, right, we've got this rig, can we do some tests? And I said, yes, got a postgrad student once again, and we started looking at magnetite systems for coal. The major objective of the study was really to look at coarser magnetite, and I'll come back to that one. Moving away from fine milled magnetite in the order of 90 micron and going to a coarser magnetite, which is much cheaper, and the losses are much lower because you don't have that much carryover. So there's economic benefit in that one. I'll show you what happened there. In the meantime, Economics Innovations developed a spec-sep system, solenoid system for this very purpose, and that's a commercially available unit. And you can see, I'll show you on the next slide, you can see the solenoids around the cyclone there. So it was a pump-fed 165 millimeter polyurethane cyclone in a closed circuit. Just zooming into that one, the red circle shows there are three solenoids in this cluster. Those are the spec-seps. And the reason we use three was it's easier to use the three and switch them on to simulate the solenoid being in a different position. So we could switch on and off and vary the current through each of those independently and look at the effect of that one. Otherwise, it's a standard messy old cyclone. Very difficult. You can, maybe at this point, I must just show there that you've got the overflow pipe there. That's the overflow going in there. That's the, that's the underflow. That's the overflow. And to sample there is almost impossible. It is a bucket, and you stick your bucket in there, you run away with a bucket, and you're full of magnetite. Magnetite takes about a week to come out of your system, your pores and your ears and your hair and everything. Terrible stuff. So we couldn't do a lot of accurate work there, but at least we could measure the densities. We couldn't measure the flow rates. And we did some tracer tests on this as well, which was, again, pretty hairy, but it worked. It was work. And the objectives was really, are we seeing an effect in the density differential? Because that was the easy one to measure. And hence, by proxy, the separation sharpness. Can we change this, the cut point if we use tracer tests for that? And the important one was the coarser magnetite. You compare the magnetite D90 of 90 micron and the coarser one of 300 micron. Is there a difference? Can I offset the bad habits of a coarse magnetite? Because again, coarser magnetite is back to stability. Coarser magnetite will have better settling. If you take a bucket of magnetite solution suspension, put it down there, the coarser the particles, the quicker they will settle. So you've got the stability thing as well. And that's not good for a cyclone. You want it fairly stable. So that's why people use very fine magnetite and not coarse magnetite for this. But there was a claim made by the manufacturer of the spec set that you can actually go to a coarser magnetite. All right. So we changed a couple of things: the medium density, medium grade, solenoid position, magnetic field strength, etc. And we got some results. And these are just extracts. First of all, this is my famous graph with 2 points on it. I didn't want this, but the student went ahead and submitted in any case, and the externals passed it, so I suppose it's okay. The blue dots showed, sorry, the x-axis is the magnetic field strength of flux density. So that point there means the magnets are all switched off. And then if I switch on both the top and the middle solenoid, that's the of the three. That is the red dot, and the other side. We found out very quickly that the uppermost or the bottommost solenoid doesn't do much, and that's the one that's too close to the spigot. So there's nothing there. So we stopped testing that. And you could see the shaded area is the recommended density differential operational area between 0.2 and 0.5, and we could see that with, we can bring a system that's out of spec, 0.7, we can bring that in with the application of the magnetic field. So that's good news. This is the fraction of coarse magnetite. We started using, fine magnetite, that's a 0 point, and you can see it's a very low EP, and that's expected as well. That's the density differential, sorry, that's expected as well. It's a very stable medium if it's only 90 micron magnetite. And then we started adding in fractions up to 50% of the coarser magnetite. And if you didn't have the solenoids on, the density differential would just shoot off, and it would actually become much too high. But if you had the magnets on, the effect by adding coarser magnetite didn't make a difference. And that's actually, it shows you that you can probably move away from the ultrafine magnetite into coarser fractions. So that was good. That was good work there. What does it do to the EP? And the cut point, once again, because we've got manual traces there, and the intervals of the tracer, density traces, are not very good. The graphs, statistically, I don't think is that. Well, let's again say we got to be careful interpreting these results. But it looked like we could get a slight improvement. Sorry, left is no magnets, the right is the magnets on. We could get an EP improvement. I must also add that in this particular graph on the right-hand side, that is with coarse magnetite. And the purpose of these two are that I can run the same efficiency with a coarser magnetite. I think this was a 40% mix of the coarse to the fine. I can run that efficiency, or I can run the cyclone the same way by just using coarser magnetite. EP was actually improved, and the cut point, well, it stayed the same at least, if not dropped a little bit. So we haven't quite answered that cut point problem yet, or the question yet, but we know that we can use coarser magnetite. That was the main purpose of this study. Right, so the summary is that a magnetic field around the cyclone stabilizes the medium, hence decreases the density differential. EP can improve. Cut point, I say, can be influenced. I don't know whether it's go up or down. It looked like it's going down because of the De Beers work that showed it went down. But it's still, the exact sensitivity is still unknown. And that is exactly what I'm doing here. And that's what we're going to do in the ACARP project. So the optimum solenoid position, I think we've got very clear where that is. Top of the conical section, but not beyond the vortex finder, the bottom end of the vortex finder. And then very important, the coarser magnetite can be used. Cheaper, lower consumption. Right, so implications and conclusions of this work was that technology looked promising to reduce cut point possibly, and to improve efficiency, or at least reduce your cut point and keep the efficiency the same, which is probably good enough for us. But more work to be required. We need to fine-tune these things. We need to optimize that position a little bit more, although that's secondary. and the field strength as well. We have to decide whether things like, you know, other operating conditions affect the field strength or the optimum field strength. And that's where the ACARP project comes in. So we know that the Australian coal, and again, it's a C word that we don't really like to use. The coal industry wants to move away from thermal coal into metallurgical coal or export coal. And the reason for that is that it's a much cleaner coal, lower ash forming minerals. And that means that that coal product has a lower density than the thermal coal. Thermal coal, you can put any old rubbish into a power station, it'll burn it. It'll heat up the rocks and then cool down the rocks again, which is why you make such a lot of CO2 for nothing. You're just heating up rocks and cooling them down. But if you've got a cleaner coal, you can actually have more usable energy going into the power station or metallurgical processes. So we want a lower density, and therefore we want a lower cut point. And that is a bit, that's what we want. It's a lower cut point. There are cut point limitations with existing plants. You can only affect the cut point so much before you run into stability problems, for example, or the geometric design of the cyclone will limit you on that one. So the holy grail is to lower the cyclones, and that's what we're chasing. Lower medium density and the stability issues. Okay, the objectives of this project will be to determine the lowest attainable cut point, associated separation efficiency, and we are also going to check whether this coarser magnetite thing will work as an objective B, but it is still very much part of our planning to try the various grades of magnetite. The equipment, this plant from Multotec has been shipped over and it's sitting in Multotec, Australia. They're busy rewiring it and getting it certified for installation here at the JK in the pilot plant downstairs. And that we're going to start on that. So if you see this funny beast standing down there, it's mine. But Multotec has already said they are designing a new rig for us for, you know, a couple of these, and that's what it looks like. It's a huge thing. We looked at 3-4 meters high. I don't think Mitch is going to be too happy to have this thing sitting on his front porch, but we'll talk to him nicely. This is a proper installation. It's big. It's got a big enough sump. The sump is well designed, and very important, where you have your over and underflow. There's going to be a sampling trolley there where you can use it on wheels, and you can actually move out a trolley, and the samples are taken, diverted into buckets or whatever, and you push it back again, so that you can do proper sampling at the same time, over underflow at the same time, because that's also an issue, because there is variation in a cyclone operation. And also you can do flow rates on that one, bucket chemistry. The nice thing as well is that we will build in sieve bins there, or baskets at least. We're still planning on that one to capture traces, so that we can do proper tracer tests on that as well. Come back to the traces now. So I'm very much looking forward to this new rig that will appear here towards the end of the year. On tracer tests, to determine cut points and proper partition curves, you need to have trace. You have to have some sort of indication of density particles and where they land, up or down, and how much of it goes up and how much of it goes down. Now, traditionally, one would use plastic tracers of different densities. These things are color-coded. You get them in different sizes. Different colors mean different densities, and you just chuck them into the cyclone and they will go round and round, and you catch them, you recover them by hand with a sieve, and you wash them, and you sit there till 12 o'clock at night counting traces, which is very tedious because a lot of these colors are the same. And so, you know, we've got the guys, Chris and Ryan from Partition Enterprises here as well, who are experts in this, and they can attest that counting traces is not the best way of spending your evenings because of this. Very, very time consuming. So we come up with a new suggestion, and that is the radio RFID traces that we are looking at. There's a radio transponder embedded in each tracer. They're all the same color, it doesn't matter. And you've got different densities, and coded onto this radio transponder is the density of that particular tracer. It's not, and then you have sensors that you can place anywhere, overflow, underflow, that picks up if the tracer comes past, and that tracer tells us, listen, here I am, I'm a 1.65, and you register that. And actually the partition curve is then just, if it's a closed circuit, tracers, the same tracer goes around and round and round. You only need a handful of tracers because the same tracer will do the same job. And if it's a near dense tracer, it'll go up 3 times and down 7 times. So you've got your 70% from the same tracer. And I'm very much looking forward to that work. So it's expensive. It's more expensive, of course, but you need fewer tracers because you use the same tracer that goes around and round and round. No manual sampling, much more accurate results. And then, Chris, if I may, I could just show you what Chris sent us. We are manufacturing 4mm radio tracers at the moment. You can probably see there are ball bearings, little ball bearings in there, in the plastic that gives you your density. So various densities, and then the transponder on the inside as well. So it's the first time we are manufacturing these 4mm tracers. Normally the tracers are big for coal, but these are going to be exciting. And if it doesn't work, we'll go back to the normal plastic tracers, and I'll get a postgrad student to count the colors. Just finally then, on the work plan and the timelines, Q3, where we are now, move and commission the old rig. It's here already. It will be on site in the next 2 weeks. And then we'll do, obviously, the OHS and the risk analysis on this. We've got a lot of experience in South Africa running this thing, so it's really just adapting those conditions to the Australian ones. Q4, we will start testing. We've got the magnetite coming from Martin and Robson. I can just give them a call and it'll be here in 2 days. And then we'll start again, repeating a lot of the Multotec work, because I want to confirm that it wasn't, I'd like to see that again. The magnetic strength, as well as the position on the density differential for starters. Hopefully we can do some tracer tests in this old rig. I'm not putting my mind on it, but if we can just at least get the density differential effects sorted on the new rig, on the old rig, then I'll be pretty happy. And then going into next year, we should get the new rig that should be commissioned, and we can then optimize the lowering of the cut point. And then we're going to play with this thing. You have a setting, you play around and see whether, and you can do that virtually online because the tracers are going around and they're being cutted, and you can turn the dial, you can see how your, hopefully, Chris, you can see how your partition curve is going to change. If not, we've got plan B. And then by Q2 next year, we are going to check this coarsening of the magnetite effect, see whether it actually works, and see whether there is any merit in moving away from the ultrafine magnetite to the, I think it's called fine. Strange, they talk about ultrafine, superfine, and fine. Those are the 3 grades you get. And then this time next year, the project should be concluded. Final report submitted, and then I'm on my aeroplane back to Northwest University. We would like to, depending on our results, we would like to ask for a continuation of the ACARP project. Hopefully move this rig to a site, a coal mine, and then take a bleed off stream from coal and run it on real coal as well, because we're not going to handle coal here. It's only going to be the magnetite tests. The logistics of running real coal. I mean, you've got to have 5 tons of coal in the feed, and then you have 5 tons of rubbish coal that you've discarded, and the logistics are just getting a bit bad there. So we're not going to do that to simulate the plant conditions. And with that one, ladies and gentlemen, I thank you very much.
All right. Thank you very much, Quentin, for a very interesting presentation. As a geologist, the background on dense medium cyclones was much appreciated. Thank you very much for that.
At least one person.
Yeah, thanks for that. And I'll open the floor for questions. Anyone? Tim?
Firstly, welcome back. It's nice to see you again. So this is a really interesting project, and I'm glad that you've conjured some money out of ACARP to have a look at this technology, which, as you said, has been around in the background for a long time. In fact, I'd add one piece of work. Rapid Magnetics in the UK did work on a similar kind of cyclone, I think in the 60s and 70s. So it might be worth looking that up to see how, what they learned. I've got so many questions. I'm going to leave some of them for coffee, so you can forget about having coffee. I'm going to be talking to you for a few minutes. Just a couple of thoughts. The De Beers experience, you kind of, they generally don't do things by halves, and they would have given it a good crack. So the question is, why did they give up? And, you can always use the argument of operator indifference or whatever it might be. The truth is they couldn't have seen sufficient benefit in broad terms to accommodate, the additional costs and wear and whatever it might be. So that's the real reason. And actually, diamonds is a really bad application to try because it's too easy. Diamonds has no intermediate density material, so the separation is actually easy. So it's actually quite difficult to show any kind of improvement. Coal is much more interesting, so it's good that you've got there. So here's a question for you, Quentin. I just wonder what is going on. I mean, you've tossed around these wonderful words like differential and the rest of it. And yes, there's Chris and his colleagues showed very convincingly that there are optimum differentials for coal. Too high or too low is not good. So if you've got something where you can tweak a knob and control the differential, it sounds like that's a good idea. I think the statistics of your experiments are very problematic. You're comparing a sharp curve against a sharp curve. Traces, as Chris will tell you, are not real coal, and you know that very well. So real coal will probably give you worse curves, and which are more easy to compare. So you're really in a difficult experimental environment here to be able to show anything. So the question is, what is actually happening in this cyclone when you switch on the magnets? It's doing something to the medium, obviously, because it's magnetic, so it's going to respond. You're seeing some evidence of a drop in differential. I think the idea of being able to go to a coarser and therefore cheaper magnetite, which has a lower consumption, by the way, the coarser the medium, the lower the consumption. So that's a good thing. But what's actually happening to the medium inside that cyclone?
I don't know.
I was afraid you were going to say that.
Yeah. I could never read anything on anybody explaining what it does. Look, it influences the individual magnetic particles, and it introduces a different resultant force onto where they would go. You've got the couple of forces inside the cyclone, as you know, outward flowing and down, and there's a zone where it's sort of zero velocity zone and that sort of thing. And it's an additional force that influences the way that the particles behave inside the cyclone. Exactly what it does, because most of the things I've seen is that they reckon the magnetic forces are pushing the particles downwards. There's an increase in the downward component, which doesn't quite make sense to me. But again, it's just one of the components. There's another component to the outward. I would guess the way that it probably impedes the outward flowing due to gravity, due to centrifugal forces, motion of these particles, and keeps them towards the center a little bit more. Hence, you will find a drop in density differential. That's what I guess, but there's a lot of thinking on that one still required, and maybe the physicists can help here. I don't know.
Can I be allowed one more quick question? I've spent half of my career in this subject, so when you get a guy like this, you've got to give him a hard time. Magnetization. So you're actually trying to, in a sense, deliberately magnetize the medium. If you put it in a magnetic field, it'll magnetize it. And some plants, particularly in ferrosilicon plants, as you know, have demagnetizing coils to stop the medium getting to that dreaded word viscous.
Yes.
do you think there's going to be an effect here that might be good or bad? Are you going to have to demagnetize the medium as it goes round and round?
We're keeping that option open on the new rig to put a demag coil on it. My guess is that because magnetization in an industrial sense occurs on the magnetic separators, which are very high, high intensity. I'm not sure if the intensities of this solenoid is high enough, but again, we'll have to see. We'll probably see the evidence. We could never see evidence of in a closed circuit of magnetization. Up to the pilot work that we've done, we didn't see that at all. But it's always easy to stick a demag coil on the feed.
Yeah, thank you. I'm on. Yeah, thank you, Professor. And wouldn't it be nice to have a magnetic cyclone that is polymer and set up with X-ray tomography? And you may find that your magnetite's concentrated where the solenoids are and the underflow is actually lower density or whatever.
I was actually thinking about that old cyclone that used to stand here with a gamma ray tomography on it. I think, Tim, it was yours. It would give us beautiful answers if we can see that. Yeah.
I'd really like to suggest that, because our CFD team here is really looking at building CFD things of different machines so you can better understand what's going on. I think it'd be really good to try to maybe work in collaboration with that team, make sure you're getting the data that they would need to, and we could potentially find some funding somewhere, maybe even in ACARP, to do a validation of your data using a CFD approach, and then we'd be able to see everything in there. And that's what excites me about CFD, is you can actually then start to answer some of these questions, and once you have understanding, you can then go to better design. So yeah,
We can answer Tim's question of what happens actually inside. That'll be brilliant. Thank you very much, Kim. Certainly. Yeah.
Any other questions on the audience?
no, I'm really excited by your technology, so we need to talk afterwards. But those radio tracers, I'm also keen on them for other things we're doing in the coal world. How fine do you think we can go with them?
Chris. 4 mil.
Thank you. Yeah, these particular ones are 4mm cubes, and with the technology that we have in them, like we're used to working with larger tracers on conveyor belts, and we can detect them from a metre away. Now these ones, we're using a quite different technology, and we know that we're going to be able to capture those traces. So the technology in these will only, and the readers that we're using will only read from a few millimetres. So that's a drawback in a lot of applications. We could possibly get down to about 2 millimetres, but those problems will multiply dramatically. So that's where the technology is at present.
I have a question regarding the magnetic field, magnetic strength. Look that from your graphs, the strength is quite low. It's come to 100 Gauss-ish. As we all know, with the distance going away, it will be quickly dropped by the strength. But look that it's quite distance from your cyclone with your 250 mil cyclone. So when do you think, what distance actually is going to affect of the media inside?
You mean the distance toward the center of the solenoid?
Yeah. Because your coil is actually around the cyclone. Yeah. And the Gauss is quite low. Yeah.
Before we're going to use that, we are going to run a calibration on the magnetic field strength inside. Let's just say a hollow cyclone where the magnets activated at various. We have to do that in any case, and then we can look at the variation, depending on where you measure inside the circle of the solenoid. But yes, there is an effect. There is an effect. Maybe that is what's changing. That's a very good point. We haven't looked at the two-dimensional plane inside and seeing what that what the density differential there is, but that's where the CFD can tell us.
So because I'm from Longy Magnet, we have some electromagnetic illustration column that apply for magnetite separation.
Okay.
So it's using that magnetic force, but a little bit higher Gauss than your ones, but we're using that to magnetize the particle, let them agglomerate together. That's another question I'm having. Whether there will be any agglomeration effect since you apply the magnetic field, will there be any, the magnetite dense media, will it be magnetized? While the magnetized attracting each other, will that has any impact of the separation? Yeah.
It will have an impact, and that comes down to the question of putting a DMAC coil on that, because if you don't have a DMAC coil on industrial systems, just the dense medium cyclone, because your magnetite is being recovered by high intensity wet magnetic separators, or higher, not high intensity, but higher magnetic separators. So you do have a residual magnetism in the particles, and they do tend to agglomerate. They do tend to form, globules, and that affects your stability. Whether this is, as I said, I don't think this is high enough to cause that, but yeah, that's just my feeling.
Thank you.
Any other questions in the audience? Actually, I have a curiosity question. So you show like the test work on, I think on different size fractions to extract the diamonds. And I think the final fraction is above 0.25 millimeters.
Oh, this was coal.
Was it gold?
This one. I'll show you now.
Let's see.
There is a quick way of coming here.
Yeah.
This one?
Yeah, this one. Oh, that's cool. All right. So because I was just thinking, like, is there like a size fraction, for example, threshold for diamonds, for example, where it's not like feasible to do the test anymore? Because I work a little bit with diamonds. They were like 200 microns, and they were like quite small, and like how it would behave.
Yeah, on diamonds, there is normally a bottom cutoff size that's established through, company techno-economics and that sort of thing. But coal, it doesn't really matter. Fine coal is problematic to work with, yes, because it's wet, and to dewater fine coal is extremely difficult. It's like a mud, like a clay. To dewater coarser coal, it's easier, and you have to dewater coal. You can't send wet coal into a power station. It's just heating up the energy. So on coal, normally plants would actually discard the ultrafine coal because it's too difficult. So I wouldn't worry about the -5. Oh, there are technologies that's looking at the -5, yes, but in practice at the moment, anything below 1 is sort of, it's dicey whether you're going to make enough money to introduce the technology there.
All right. Yeah. Any other questions? All right, Mark.
Yeah, thank you very much, Quentin.
Sorry,
yeah,
I
just
disappeared. I dropped my pointer.
like a Punch and Judy show, right? Yeah, just going to say, I remember working in the coal operations in South Africa and dealing with fine coal. It was interesting in the sort of, showing my age, but back in the 80s or so, we'd pretty much discard that fine coal until we discovered it was, 5, 6, 7, 8% of product. And then we looked at the cost benefit analysis, because a lot of in thermal coal, the heat energies, actually there's a plenty in the fine. The fine is a really good quality. It's just problematic. And so there was a lot of effort put into, adding 5% more product at a better heat got you a good product if you could dewater. So really interesting. And, trying to work that out as to just how to do that, because ultimately in the power stations, what they do is they basically mill it and blast in a pulverized dust into the boiler. So it's ultimately fines that go in, but they dry. So interesting.
Yeah, problems in transport as well. To transport the wet coal, there was a story, I've seen pictures of this, where fine coal was on the back of a railway truck, And they couldn't tip it. They couldn't get it out because it formed a block of cement, you know, with the shaking and everything. No, it's problematic, both from an energy point of view as well as a handleability point of view. No, lots of debates about where do we go with fine coal.
All right. Do you have any other questions? If not, thank you very much, Quentin. I'd like everyone else to end your thanks, Quentin, again for his presentation.
Thank you.
Cheers.
It's a pleasure. Thank you.
And next week we have John Atherton from Acacia Energy presenting about renewable compensation in 2024. So hope to see you all there. Thank you.